The sinking never stopped, but it slowed, exactly as engineers hoped.
Japan's famous floating airport, Kansai International, is slowly sinking into the sea.
For the smart Japanese engineers, this is not a big deal.
All readings are stable, well within the safety margins.
Excellent. The surface integrity looks perfect for the morning flights.
Years later, additional stairs had to be added to fill the gaps caused by settlement. This modern engineering marvel sinks about 6 centimeters into the sea every year.
Beneath the airport lies a thick, waterlogged clay layer, challenging engineers to create a stable foundation.
Imagine erecting a massive airport on a seabed as soft as a wet sponge. A monumental challenge indeed.
This was the exact challenge faced by Japan's Kansai International Airport, constructing a stable facility on soft seabed.
The enormous weight of the airport gradually squeezes water from the clay, strengthening the seabed over time. Engineers needed to predict how much the soil would settle under the immense weight of the airport.
Predicting soil settlement under the massive airport load was a huge challenge for geotechnical engineers.
The settlement process is gradual, taking years to fully stabilize the island beneath the airport. Engineers analyzed 3 potential settlement scenarios to anticipate possible outcomes.
In the best-case scenario, the island remains safely above sea level after settlement.
A situation every engineer dreams of. Plumong, stability and safety achieved. In the second scenario, the island could sink below sea level, a challenging situation to remediate. Such a condition would be extremely difficult to fix without major intervention.
And in the worst-case scenario, the soil may never fully stabilize, posing a long-term risk. Estimating soil settlement was a monumental challenge for the geotechnical team.
Steel chambers were carefully installed at corners to support the enormous seawall.
Engineers moved millions of cubic meters of earth from nearby mountains to build the artificial island.
Giant barges transported the earth over 28 kilometers, operating continuously for years.
Piles were driven into the seabed to form the backbone of the bridge, connecting the island to the mainland.
Double-decker steel trusses were installed, allowing trains below and cars above, with flexible joints to withstand ocean currents. The solution was radical yet brilliant, placing the entire terminal building on adjustable, detachable pillars.
Using hydraulic jacks, engineers could precisely raise individual pillars whenever uneven sinking was detected.
By lifting only the affected sections, the terminal was saved from structural disaster.
However, lifting the terminal introduced a new challenge. The staircases could no longer reach the ground.
To solve this, engineers added extra stair sections to bridge the newly formed gaps.
Once the lift was complete, workers immediately locked the structure in place by tightening the bolts.
Despite these measures, the airport continues to sink by nearly 6 centimeters every year.
Remarkably, authorities decided to construct an entirely new island runway, despite the ongoing sinking of the first.
The second island, completed in 2007, sinks even faster at nearly 21 centimeters every year.
The second island, completed in 2007, sinks even faster at nearly 21 centimeters.
answer to this bold investment lies deep beneath the ocean floor. The answer to this bold investment lies deep beneath the ocean floor.
Engineers used an advanced ground improvement technique known as sand drains.
Engineers used an advanced ground improvement technique known as sand drains. The immense weight of the airport slowly squeezes water out of the clay, strengthening the seabed over time. Engineers evaluated three possible outcomes: stable settlement, dangerous submergence, or endless sinking. Engineers evaluated three possible outcomes: stable settlement, dangerous submergence, or endless sinking. Predicting the final settlement required years of experiments and newly developed testing equipment.
The most accepted prediction estimated nearly 19 feet of total settlement.
The existing mainland airport was overcrowded, noisy, and surrounded by residential neighborhoods.
Race. Building on land was impossible, leaving the sea as the only viable option. The Kansai region is exposed to powerful winds. Building on land was impossible, leaving the sea as the only viable option. The Kansai region is exposed to...
Underwater divers performed one of the most dangerous tasks, preparing a stable base deep below the sea.
These armor stones formed a stable foundation for the entire seawall structure.
Layer by layer, lower and upper mounds were constructed to shape the artificial island's perimeter.
Cladding stones were added to protect the structure from erosion and wave impact. It took nearly 2.5 years to complete this massive defensive barrier. At the corners, steel chambers were driven deep into the seabed to ensure structural integrity. With the seawall complete, Middle Eastern engineers faced the monumental task of filling the island with earth. Over 180 million cubic meters of earth were quarried from nearby mountains to create the island. Entire mountains were carved and transported toward the sea to give birth to an artificial island. These giant barges carried the earth across nearly 28 kilometers of open sea. Day and night, the barges entered the seawall zone without pause.
In one stroke, millions of tons of earth were released into the sea.
This operation ran 24 hours a day, 7 days a week, for years.
Gradually, the island began to emerge from the ocean.
Simultaneously, engineers began constructing the bridge connecting the island to the mainland.
These piles became the backbone of one of the longest airport bridges in the world.
Giant floating cranes performed this delicate and dangerous operation at sea.
The bridge was designed with a double-decker structure, carrying both trains and vehicles. Flexible joints allowed the bridge.
With the island rising, engineers turned their focus toward the terminal building.
Model-based experiments revealed a hidden and dangerous problem. To study the solution, engineers created micro-hydraulic jacks with extreme precision.
Hundreds of CNC machines worked together to produce flawless components.
Each hydraulic jack was engineered for absolute control and reliability. The heavier wings caused uneven settlement, threatening structural integrity. The solution was simple in concept, but complex in execution. Sensors and computers guided each lift with microscopic accuracy. Once stabilized, the building returned safely to equilibrium.
Flexible joints allowed the bridge to survive relentless ocean winds and shifting forces.
With the island rising, engineers turned their focus toward the terminal building. Model-based experiments revealed a hidden and dangerous problem. To study the solution, engineers created micro-hydraulic jacks with extreme precision.
Hundreds of CNC machines work together to produce flawless components.
Each hydraulic jack was engineered for absolute control and reliability. The heavier wings caused uneven settlement, threatening structural integrity. The solution was simple in concept, but complex in execution. Sensors and computers guided each lift with microscopic accuracy. Once stabilized, the building returned safely to equilibrium.
Engineers faced a shocking reality. The sinking hadn't stopped, raising global concern.
News outlets branded the project as a historic engineering blunder.
Instead of heavy concrete, the building relied on a visible steel skeleton for strength without excess weight. The lighter terminal floated above the island. Engineers ensured it would sink at the same pace to prevent foundation exposure.
During the 1995 Great Hanshin earthquake, innovative sliding joints protected the terminal, leaping it.
Piles formed the backbone of the bridge, anchoring it securely to withstand ocean currents and earthquakes. Piles formed the backbone of the bridge, anchoring it securely to withstand ocean currents and earthquakes.
Giant floating cranes place steel trusses, forming the bridge's double-decker structure for cars above and trains below. The flexible joints allowed the bridge to withstand deadly ocean currents and high winds.
Micro-hydraulic jacks helped simulate terminal settlement, ensuring precise structural adjustments.
JLC CNC provided precise components, enabling flawless testing and adjustments.
Additional earth was added, using every compacting technique to maintain the airport above sea level.
Kansai International Airport stands as one of the boldest engineering experiments ever attempted by humankind.
Hidden beneath the terminal, thousands of adjustable pillars constantly fight gravity and time.
Below the waves, sand drains quietly squeeze water from the clay, strengthening the ground year by year.
Massive tetrapods absorb the ocean's fury, protecting the artificial island from relentless storms.
Entire mountains were moved, grain by grain, to create land where none existed before. This bridge became the lifeline between the floating airport and mainland Japan. Renzo Piano's design allowed air, light, and people to move effortlessly through space. A lighter structure meant less pressure on the sinking island below. To match the island's movement, engineers added weight where it mattered most.
When disaster struck, Kansai Airport proved the strength of Japanese engineering.
Even as the ground moved,
the airport remained operational.
In crisis, the airport transformed into a lifeline for millions.